In Chapter 24, we will be looking at carbohydrates. And the picture that you see here is a very germy hand, all kinds of gross stuff on it. There's white cream that is there, which is an antibiotic cream called neosporin or bacitracin or something similar. One of the three active ingredients is called neomycin, which is a carbohydrate derivative. And in this chapter, we're going to look at some of these different carbohydrates. Carbohydrates are commonly referred to as sugars. The chemical definition is different than the definition or something that you've heard of outside of chemistry. So carbohydrates for everyday people are bread, potatoes, those types of things. In chemistry, it's referred to as a sugar. They are abundant in nature and are in several of the foods that we eat, and they're also building blocks for living organisms. These are naturally synthesized in nature from carbon dioxide and water via photosynthesis. So carbon dioxide, 6 moles of that plus 6 moles of water plus sunlight gives us glucose. A monosaccharide is a single, simple sugar. These contain multiple chiral centers, and we often use Fischer projections to represent their structure. So instead of drawing a long chain with alcohols here and there, we use these Fischer projections to show their structure. So the first one we see here is glucose. The alcohols are on specific sides of the molecule, and we have fructose. The difference between glucose and fructose is the carbonyl functional group. In glucose, we have an aldehyde at the top, and fructose contains a ketone. An aldose is a sugar that contains an aldehyde group, which is why it has the prefix aldo. And that ose ending is what we use for sugars. And ketose is a sugar that has a ketone group. The terms di, tri, tetra, pent, hex, hept indicate the number of carbons. So this is how we can classify monosaccharides, by the functional group and the number of carbons. A sugar with an aldehyde functional group is an aldo. And then we use the number of sugars, which is 5 or pent. And that ends in ose for the sugar. A 6-carbon sugar with a ketone is going to be a ketohexose. And that is the general classification of monosaccharides. Glyceraldehyde is the simplest aldose. It has one chiral center. This one here on the left is D because the OH group on the last chiral carbon is on the right side. So D is for right. And L-glyceraldehyde has the OH on the left side. So the D sugars have OH groups at the chiral center farthest from the carbonyl on the right-hand side in the Fischer projection. So D-ribose, D-glucose, D-fructose, those all have the sugar, the OH on the right side in the second to last carbon or the last chiral carbon. A D sugar means the configuration is R, while an L sugar has the S configuration. So these all have stereochemistry of R. So you could go back and assign all of these as R or S, but the really important thing here is that last chiral carbon, and that will determine if it's D for dextrorotatory or L is for levorotatory. So there are 4 possible aldotetroses. 2 of these are D sugars, and the other 2 are the enantiomeric L sugars. The enantiomer of this one would just be the mirror image. So this is an L sugar, this is D. And that one is L. We started with D-glyceraldehyde, And if we add one carbon to that, that's going to add another possible stereocenter. So now we have two possible configurations. If we add another carbon to the threose or erythrose, that is going to add more possible stereoisomers, and so on and so forth. So we have 6 carbons, there are 8 different stereoisomers. So with ketoses, the possible number of stereoisomers is slightly less because now one of these carbons is tied up in the carbonyl function. So with 6 carbons, we only have a possible of 4 stereoisomers here. So each of these, even though they all had the same formula, these are all stereoisomers of each other, they differ from each other in 3D space. So an aldehyde can react with an alcohol, which we've seen before, to produce a hemiacetal under protic conditions. So if you remember back to your aldehyde and ketone chemistry, if you react an alcohol with a ketone, we have a hemiacetal that forms, and that can further form an acetal. But the hemiacetal is when we have an OH plus an OR. A cyclic hemiacetal can form, and that favors a 5 or 6 membered ring. So you can imagine this OH coming around to attack here, where we have the OH. This is putting it into proximity of the aldehyde. And under acidic conditions, in equilibrium, the hemiacetal is favored. And that is the new bond that is created. This is a cyclic hemiacetal. So we have the acetal carbon that has one OR group where the rest of the ring is the R, and then the OH group there. Monosaccharides can undergo ring closing hemiacetal formation, which we just saw. The new chiral center formed is called an anomeric carbon, or carbon 1. When we draw these cyclic forms, which are referred to as Hayworth projections, we start with numbering the carbon chain here. We have 1 through 6. So this is the same thing. I'm just going to draw them in proximity. I'll try to keep the colors the same here. So here's my aldehyde. This is carbon 1, 2, 3, 5. On carbon 5, we have a CH2OH. This is the OH that's on carbon 5. This is the open form. And you can imagine that oxygen lone pair attacking this aldehyde. Okay, so the alcohols, where do they go, up or down? So this is kind of a flat ring here. Think of that as wedge. The whole ring is flat. Any alcohols on the right side are going to be pointing down. So these alcohols here point down in the ring. So it's right down or down right. And alcohols on the left carbons are going to be up. So left, up, down, right. So at carbon 2, my alcohol's on the right, so it should be pointing down. There's an H here that is up. At 3, it's on the left side, so this should be up, which means the H is down. At 4, the alcohol is right, so it is down. This is up, and on 5, we also have a down hydrogen here. The hydrogens I'm less concerned about as long as you know where the alcohols configure themselves. Once the alcohol bonds to form the hemiacetal, we're going to form the cyclic structure. So that is the oxygen that was there. I had a CH2OH. I'm just going to draw the alcohols in here. I'm going to ignore the hydrogens. But the OHs just carry over from the last structure over here. So this is the closed form. And one thing that I am missing is the OH at carbon 1, and that can go up. So this is 1, 2, 3, and that one is 6. So C1 is the anomeric carbon. So the OH can be up or down at the anomeric carbon because this alcohol here in the open form can attack from either face. If the OH is pointing down, that alcohol is down and it's swimming with the fishes. A fish looks like alpha, so this is the alpha anomer. If the alcohol is pointing up, it is flying around with the birds and the butterflies, which looks like a beta. That is the beta anomer. So this one flies. All right, so your beta could look like a bird or a butterfly. In either case, if the alcohol at the anomeric carbon is up, then we have the beta anomer. If it is down, we have the alpha anomer. So these 6-membered rings are referred to as Pyranose rings. And these are also referred to as Hayworth projections. Okay, a Pyranose ring is either drawn as a Hayworth projection or a chair conformation. And the chemists tend to like chair structures better, just because we like to draw chairs, apparently. And it reveals the 3D conformation. In the chair conformations, the ring is always going to be in the upper part of the right rear position. D-glucose is the only sugar where all groups are equatorial. It's the most stable sugar and thus the most abundant in nature. So from the Hayworth projection, we can't see that they're all equatorial or how stable they are, but when we put them in the chair conformation, we can see that. And with the chair, you just transfer the downs and the ups. So this would be 1. And at carbon 2, we have an OH down. It's down here. At 3, it's up. So it's up, down, and then you can see that there. Pyranose rings are 5-membered ring hemiacetals of a sugar, and fructose will equilibrate among the pyranose and the pyranose ring. So this one can go to the 6-membered ring or the 5-membered ring. Okay, so this is in equilibrium with acid. And this is how it would attack if it was to form the 5-membered ring. Where that one is carbon 2. and that is C6. So this is the Pyranose. In the 6-membered ring, when that forms, it's the OH of carbon 6 that's going to attack, and not of carbon 5. And then you have H's on either of these. And the up and down is the same thing as we did prior. So at carbon 3, that is on the left side, so it'll be up. 4 is on the right, so that's down. And then 5, since it's part of this, is on the right, so that one's down as well. So this is the Pyranose. The furanous form of D-fructose takes part in most biochemical reactions. So that 5-membered ring is the one that we see the most often. That's the Pyranose, the 6-membered ring. So that is the Pyranose versus the Pyranose.